All right, so thank you to all the organizers. Very happy to be able to give this talk. I was at one of these seminars about a week ago, and I thought I arrived in plenty of time, and I checked the time, and it was in simony, I thought, and then the actual talk was in Flying Hall. So I raced over there and got there about half an hour late. So I was very paranoid today to make sure that I didn't make the same mistake. Okay, so
make sure you're clicked onto it.
Okay, there we go. Thanks. All right, so this is the outline, and it's first of all, I'm going to give you a statement of some known results for famous results for complex surfaces, and then talk about some some conjectures, and then I will talk about a oops.
All right.
Talk about it.
Had some issue with having everything show up on your screen.
Okay. All right.
So what I did is I just couldn't stop sharing.
Okay.
So I'm just gonna film what's on the screen there.
Okay.
Thanks. Sorry about that.
Yep. No problem. Okay. So so for one of these conjectures, then I'm going to describe an approach using something I've studied for quite a while with Tom Ness, non-Abelian monopoles, and our progress towards this proof of this conjecture. And then the second half of the talk will focus on the technology a little bit. So the middle two sections are a little bit on the more technical side. So I will kind of tread lightly on those two sections. I've tried to make them complete in case somebody wants the slides and would like a complete story. And then the last section is really a pictorial introduction to some of the ideas and how they work. So I hope to get to spend more time with that. All right, so this is based on a couple of papers. One is a monograph that was about a year ago with Tom Ness. And then the second is, I'd hoped to have it finished by Thanksgiving, but didn't quite make it. A paper that I hope to submit at least by the end of the year. And then there's ongoing work that's also joined with Richard Wentworth and Tom Ness. All right, so let me talk about the motivating conjecture to begin with. So this is a result that's due to Miyaoka and Yau independently around about the same time, 77, 78, something like that. Miyaoka's proof is entirely using algebraic geometry. Yau uses PDE methods to get the result. And the result is very concise. Simply says that the first Chern class squared of the holomorphic tangent bundle is less than or equal to 2 times the second Chern number. So in fact, this is a purely topological inequality, as I'll explain in a moment. Both the right-hand side and the left-hand side can be expressed entirely in terms of Betty numbers of the underlying real four-manifold. So the way to think about this inequality is a kind of topological constraint that arises because you know that your real four-manifold is actually has the structure of a complex surface of general type. So if you don't know anything about the classification of complex surfaces, that's fine. I don't know a whole lot either, but I'll just say that this inequality also holds for other complex surfaces, and a little list of them is given there at the bottom of the page. And a weaker version of this inequality was proved by Bogomolov, I think a little bit earlier, and that's why it has the B and Y name attached to it. So it's been a question that's been explored for decades now, and at least in the symplectic four-manifold community, as to whether or not a version of this inequality holds for symplectic four-manifolds. And I want to talk a little bit about the efforts towards a proof of that conjecture or finding a counterexample. So first of all, I mentioned that this inequality could be expressed purely in terms of Betty numbers, and I want to make good on that promise. So first of all, if you read the books on complex surfaces and the like, then you find that C1 squared can be expressed in terms of the usual Euler characteristic of the four manifolds and the signature. Similarly, this quantity chi sub h that it's called a so-called holomorphic Euler characteristic that topologists often like to rewrite the inequality I had in the previous page, also expressed in terms of essentially Betti numbers. And that expression in terms of Betti numbers is given here. Now we're going to aim towards a proof of a version of this inequality for symplectic manifolds with certain properties that symplectic manifolds happen to have. But I'm going to phrase the conjecture in a little bit greater generality. So it will include symplectic manifolds, but they will have these, these properties. Okay, so we're going to call a four-manifold standard if it has just a bunch of properties that happen to be good for doing gauge theory on, so Seiberg-Witten theory or Yang-Mills theory, in the sense of Donaldson theory. So it's closed, connected, oriented, smooth, and it has odd self-dual Betti number, bigger or equal to 3, first Betti number equal to 0. And this last constraint is not something we feel is essential, but it makes life a little bit easier. All right, so here's the conjecture. I'll explain why it also includes symplectic four manifolds in a moment. So the conjecture states that if you have a standard four manifold of so-called Seiberg-Witten simple type with a non-zero Seiberg-Witten invariant, then this inequality holds. Now, I've written this inequality in the way that topologists usually like to write the BMY inequality, but it's the same inequality. It's just written in the way that topologists prefer to write it. And this conjecture it's a generalization of ones that are stated for symplectic four manifolds to go back to Ron Stern. Gomp and Stipschitz has a version of it as well in their book on four manifolds. I think Janusz Koller may have a version of it too, and in a paper he wrote some years ago about generalizations of the BMY inequality. So why do the hypotheses include symplectic four manifolds? So if you have a symplectic four manifold, Taubes showed many years ago, right around the time that Seiberg-Witten theory was invented, that they have a Seiberg-Witten simple type, a property that I won't explain. I can if somebody wants to ask me about it. But they have non-zero Seiberg-Witten invariance. That's the crucial thing. So they satisfy the hypothesis of the conjecture. On the other hand, you might wonder, well, are there four manifolds with non-zero Seiberg-Witten invariance that are not symplectic four manifolds? And it's a famous early result of Zoltan Szabo that there do exist such four manifolds. So it makes sense to try to phrase the conjecture, the way that I've stated it. We'll see shortly that it's also a natural conjecture based on circumstantial evidence that's lying out there. So there's been a whole series of efforts by topologists over the years to construct counterexamples if they can to the inequality. So symplectic four manifolds whose characteristic numbers violate the BMY inequality, or find a proof that's intrinsic to symplectic four manifolds. Naturally, neither a proof nor counterexample has surfaced so far. On the other hand, if you kind of break some of the hypotheses, so you drop the requirement that the four manifolds have non-zero invariance, and it's very easy to find a counterexample. So you can do this with connected sums of the complex projective plane, for example. So, and let me just talk a little bit about some of the work that's been done so far. So Simpson proved this inequality using the generalization of the Higgs monopole equations that Hitchin had studied over Riemann surfaces. Simpson essentially studied them over complex Kaehler surfaces. And Lebrun Lebrun has proved inequality for Einstein four-manifolds with non-zero Seiberg-Witten invariance. Cohn and Liang has obtained some variance of the result as well in special cases. And there's a program that Gang Tian and his collaborators have been working on, I think, for some years that tries to use a notion of symplectic curvature flow to prove the inequality. I'm not sure, what the status of that is. But there's a nice undergraduate thesis where the idea is explained. So it was supervised by Tian. Okay, so so I'm going to talk first of all, after that introduction, about our approach to proving the inequality. So it's fundamentally analytic in nature. Yau proved the inequality by demonstrating the existence of a certain solution to a Kaehler-Einstein equation and used a Chern-Bay inequality. So we replaced the Kaehler-Einstein equation effectively with a version of the Yang-Mills equation. So we're interested in proving existence of a certain Yang-Mills equation with rather tight constraints that I'll explain shortly. And then the inequality will come from, in fact, an unexpected place, the expected dimension of the moduli space of a certain moduli space of anti-self-dual connections over a suitable bundle. So underlying the B and Y conjecture for symplectic or manifolds or Seiberg-Witten simple type manifolds, there is an analytic conjecture that's the real kind of engine of the proof, underlying the proof. So I'll explain the engine and then how the B and Y inequality follows from this engine. So let's suppose that over our four manifolds, we have a rank 2 Hermitian bundle, and its first conjugation number satisfies an inequality. Now, if you translate this inequality on the first conjugation number into the so-called instant number that you read amongst other places in Karen's book from Dan Fried many years ago, it says that you're interested in SO3 bundles with a small instanton number. I'll talk about why that's significant in a moment. And then the conjecture is that if the first conjugation number obeys this inequality, you can still find an anti-self-dual connection on that SO3 bundle. So there's a certain amount of technology associated with anti-self-dual connections, Yang-Mills connections, and so forth. And I'll just sort of sweep that under the rug and regard it as kind of known, even though many of you may not necessarily know what they are. All right, so let me explain why this is an interesting conjecture or why a solution to it is relevant. So over a four manifold, you can, if you're given a rank 2 Hermitian bundle over a four manifold, you can attach to that a moduli space of solutions to the anti-self-dual Yang-Mills equation. And this moduli space is expressed here. It's a set of solutions to the anti-self-dual Yang-Mills equation modulo gauge equivalence. And this is due to an early result of Karen. This is a smooth manifold with given certain conditions. This is a smooth manifold, provided, for example, the Riemannian metric is generic. That's not essential for our program, but it makes at least the initial idea easier to explain. And in particular, it's finite dimensional. Now, the important feature of this moduli space we're going to use, well, going to be two things we're interested in. First of all, knowing that it's non-empty. The second thing we're interested in knowing is what's its so-called expected dimension. And its expected dimension is something you can compute using the Atiyah-Singer index theorem. So you can read about how to do that in for example, Karen's book or Donaldson and Kronheimer and so on. And they will express their formula possibly in a different way. But this is essentially the formula you can read in, for example, Donaldson and Kronheimer's book. And what by expected dimension, what they mean is that if this manifold, if this set is transversely cut out as a smooth manifold, then that's the dimension of the manifold. The actual true dimension, there you go. All right, let's suppose then that this conjecture holds. So this SO3 bundle does support an anti-cell dual connection such that this, whoops, sorry, wrong way. This special kind of topological constraint holds. Then it's a smooth manifold, it's non-empty, so its expected dimension is non-negative. It's the actual dimension. And then you just turn this inequality around. 1/2 the expected dimension is this quantity here. And now on this, and to get this inequality here, I've just plugged in what I've called this, this topological constraint on the original SO3 bundle. And then out pops the B and Y inequality. So you can contrast the logic with work that's been done many years ago by Taubes and others. So Taubes famously proved the existence of anti-cell dual connections when the so-called instanton number is sufficiently large. So the novelty here is that we're claiming we can find instantons even when the instanton number could be quite small because it's constrained by a topological upper bound. So we're going to prove conjecture 2 using a sort of a Morse theory on steroids type of approach. And it's that Morse theory idea that I want to describe today and some of the ingredients involved. So some of these gauge theoretic ingredients are not necessarily familiar to everybody. So I will kind of skate over the details of these gauge theoretic equations because they're fundamentally kind of not essential, at least for a first understanding of what the idea is about. So I'll simply say that there is a set of equations, which is in the middle here, equation 6. They generalize 2 famous equations in gauge theory. So one is the anti-cell dual Yang-Mills equation, and they also simultaneously generalize the Seiberg-Witten monopole equations from 1994. So, and they've been given various names. We sometimes call them SO3 monopoles or non-Abelian monopoles, and these slides are called them non-Abelian monopoles. And the main distinguishing feature of them, what makes them non-Abelian, is in the Seiberg-Witten case, this bundle E is a line bundle, whereas we're allowing it to be a rank 2 or higher bundle. We only need rank 2, but it's important that it's not just a line bundle. That's what allows it to simultaneously extend the anti-cell dual equation and the Seiberg-Witten monopole equations. And it's formally it looks very similar to the Seiberg-Witten equations. There's a Dirac operator. There are coupled spinners. So if you're familiar with the Seiberg-Witten equations, it's not a big leap to write these equations down. And there are equations, for a pair, a connection A and a spinner, coupled equations. So whenever you have some nice equations in gauge theory, which are invariant under action of gauge transformations, which these are, you can form a moduli space and hope to try to extract nice properties from it. So this is what we're labeling here, Msubt is this moduli space of non-Abelian monopoles. And it was noticed early on by Princeton and Turin, Telemann and Koenig, that this moduli space splits into a nice disjoint union of pieces. So there's a piece where the section phi is identically 0. And if you flip back to the equations and stare at them, you'll see that then those equations reduce to a copy of the anti-cell dual Yang-Mills equations. Another more subtle thing happens when the connection A happens to be reducible. So it reflects splitting of the rank 2 bundle as a direct sum of line bundles. And that's more subtle. And but nevertheless, this equations, if you play with them, you find that they also reduce to a copy of the Seiberg-Witten monopole equations. So this moduli space, then you can think about it as being a disjoint union where you have a middle piece, which is most of the moduli space, and then two closed subsets, if you will, where the section is zero. There are the anti-self-dual Yang-Mills equations for that moduli space, and then many copies of solutions to Seiberg-Witten monopole equations. And one of the ways in which we use the non-zero Seiberg-Witten invariant is to say that this big middle piece, and I'll give you a picture in a moment to illustrate why it's big. This middle piece is non-empty, and that's how we use the non-zero Seiberg-Witten invariant hypothesis. And it's also known that if the geometric perturbations you can use, like the Riemannian metric and so on, if those are generic, this moduli space is a smooth manifold. The rest of it, these pieces where the section is zero and the connections are reducible, those in general will be singular, possibly highly singular subsets. All right, so let me give you a picture then of the setup of what the moduli space looks like. So at the bottom, I've written here, or I've labeled a copy of the moduli space of anti-self-dual connections with number K. And these red dots picture, they represent Seiberg-Witten moduli spaces corresponding to different reductions of the underlying rank 2 bundle E, or different spin C structures, as they say in Seiberg-Witten theory. And then everything else, aside from this blue anti-self-dual moduli space or the Seiberg-Witten moduli spaces, that's the big middle that I mentioned earlier. I've also, labeled these points in a way that suggests a Morse theoretic interpretation, as if these points are actually critical points of some kind of height function, and that's on purpose. So, I've labeled two kinds of critical points, if you will. Points up here where there seems to be some kind of singularity, and then points in the moduli space here where it looks like they're smooth points. But in every instance, these critical points are labeled in such a way that they suggest that they have Morse index positive. So they're not local minima. In fact, the only labeled points in this picture which are global minima, unlocal minima, or is this moduli space of anti-self-dual connections, at the quote-unquote bottom. So that's actually the intuition that we use. On this moduli space, there is in fact a natural candidate for a Morse-Bott-like function, which is just the L2 norm squared of the section. Now, many years ago, Nigel Hitchen had written a famous pair of papers. One of them is called the self-duality equations on the Riemann surface. And he used a Morse function. He proved it actually was a Morse function on his moduli space, which at least formally looks like this. In his case, the phi was the Higgs field, whereas for us, it's a Dirac, it's a spinor. Also, in Hitchen's case, the moduli space actually was a smooth manifold, and he could prove that this function here actually was a Morse-Bott function, and furthermore, he computed the Morse index of this function at its critical points using a clever idea that I'll get to. The formal, aside from the formal similarity, the thing to remember here is that this moduli space in general is highly singular. Okay, so I'm going to make some assumptions, that are very strong in order to get across the idea of the proof and just, see how it works in a highly idealized case. So I'm going to assume that this height function f is actually Morse-Bott on the moduli space. And that its critical submanifolds are exactly either the moduli space of anti-self-dual connections or these moduli subspaces of Seiberg-Witten monopoles. So we have, we can define a Hessian operator for our height function at the critical points, and then split the tangent spaces into three pieces: the tangent space to the critical submanifold, and then maximal positive and negative weight spaces, or spaces that really Hessian has positive eigenvalues or negative eigenvalues. Those subspaces of the tangent space, they will be tangent space with stable and unstable manifolds. And then we can define a Morse-Bott signature, which is this, consisting of the Morse index, Morse-Bott index, co-index, and the nullity. And so the observation then is if this, if the Morse-Bott index of every Seiberg-Witten critical point in this, under all these kind of idealized assumptions, if that's always positive, then the critical submanifold given by the moduli space of anti-self-dual connections is non-empty. So we assume everything possible to get this result of the moduli space is a smooth manifold. It's compact. Everything one could ideally want. So those are artificial assumptions, since they're not in general going to be true or anything even close to it. And that's just a picture, again, just a reminder of the strategy. So one thing that's worth remembering is how did Hitchin compute the Morse index of his critical points. So he used a beautiful theorem due to Frankel from 1959 or so. So he noticed that his moduli space that takes monopoles carried a natural circle action. And that his moduli space was also symplectic. In fact, that several, three independent symplectic forms, circle invariant. The function that he defines, the L2 norm square of his Higgs field, is actually the Hamiltonian function for this circle action. And then he applied then a version of Frankel's theorem, which said that if you have a critical point, it's well known that that's equivalent to having a fixed point to the circle action. The meat of Frankel's theorem is that the Morse-Bott signature is given by the dimensions of the positive, negative, and zero weight subspaces for the circle action on the tangent space to a fixed point. So this is a beautiful theorem. It applies when the manifold M is smooth. The catch in our application is that the manifolds in which the space in which we might be trying to apply a version of this theorem is in fact highly non-smooth. It's highly singular.
I have a question.
Yeah.
Just from your picture, it looks like if you're able to compute an index at the Seiberg-Witten solutions, that you actually showed the moduli space of MT is non-empty.
Yeah, the moduli. Well, we know that the moduli space is, everything. We know that there is a middle, if you will, in between the Seiberg-Witten moduli spaces and the anti-self-dual moduli space by independent calculations. But in practice, this is a highly non-compact space. So I don't.
Yes.
Yeah. So that I don't think one can.
So you're trying to prove something about topology.
No, we're actually not trying to prove anything about this topology. No.
So what will we try to do?
We're trying to prove that this moduli space of anti-cell dual connections is non-empty.
Oh, okay.
That's all we need.
Sure.
But oh, that's a non-trivial thing. Okay, so I made a bunch of assumptions here just to get across the idea. One is that the critical points, we have nice critical submanifolds which are in themselves embedded smooth submanifolds, and in fact in practice they're not. Also the moduli space of non-Abelian monopoles, this picture that I wrote, it's highly non-compact due to energy bubbling, as Karen showed many years ago in related contexts. And also, unless the underlying four-manifold has a Kaehler structure itself, the moduli space is certainly not obviously Kaehler or symplectic, almost symplectic itself. Right, so one of the difficulties one can get around, at least one has a way of addressing it using compactifications of the kind that Karen described in her book, and are also described in Donaldson and Cronenberg, and famously used in the construction of Donaldson invariants. That these moduli spaces admit a Uhlenbeck type compactification. And if you go further, if you make a stronger assumption, if you assume that the Riemannian four-manifold is actually a complex projective surfaces, then you have projections which come from algebraic geometry. So one of the assumptions we're making along the way to proving the conjecture we're ultimately after is to assume that the four-manifold is a complex projective surface, and then we can make use of more tricks from algebraic geometry to give at least an alternative path to the BMY inequality that's kind of distinct from Msubt. Of course, ultimately, we're interested in the case where where X is a smooth four-manifold. Okay, so let me switch gears a little bit and talk about a notion of Morse-Bott index that is suitable for our program and that can replace the so-called classical Morse-Bott index. And to say why we need it, let me just go back to this picture temporarily. So we know what we mean by Morse or Morse-Bott index when you're at one of these critical points here, which is classical, where the moduli space is smooth around there. However, if you're at a critical point which is singular, well, first of all, you have to say what you mean by critical point, and then it's not clear that classical notions of Morse index are going to apply, even though in some sense intuition tells you that, well, this should be a local maximum, a global maximum maybe. So we need we're after a notion of Morse or Morse-Bott index that allows us to say, regardless of the smoothness of these critical points, that if this Morse or Morse-Bott index, called a virtual Morse index, is positive, then necessarily you're at a local, you're not at a local minimum. So the point is at least a saddle point or maybe a local maximum. So that's the point of this definition, which I'll introduce. So we're going to describe two flavors of this concept. One is much easier to describe, and it's possible to to illustrate the idea using nice pictures. The version that we actually use occurs when we have a circle-equivariant setting, and that's the important one. And this, so it's going to be the Morse index, which is going to do the work for us, is what we call a circle-equivariant virtual Morse index, Morse-Bott index. And it will be tailored to analytic singular and possibly singular analytic spaces, provided we have a non-degenerate two form on some ambient manifold that contains that analytic space. And so this might seem a little bit specialized, but in gauge theory, there are lots of situations where this kind of setup arises. So it arises in Hitchin's original study of Higgs pairs over Riemann surfaces. he chose to add in a restriction that ensured his moduli spaces were always smooth. But one could apply this notion to his moduli spaces when you drop his specialized assumption. We also apply when you have moduli spaces of projective vortices, so-called over Kaehler surfaces. All right, so this, so the definition is a little bit complicated. So that's why at the end, I hope to spend some time talking about the pictures, which will hopefully get across the idea a little bit better than some of the formal definitions.
Excuse me, can you give a brief hint why the moduli space should be analytic? If you're only on a smooth manifold?
Yeah, so this goes back to results of Kuranishi. So the basic idea is that even though the manifold may not be analytic, and it has a Riemannian metric which is not analytic, the actual equation itself looks essentially like a quadratic polynomial. So it's essentially a polynomial in the underlying variables. That's the reason. So in general, analytic spaces are you can think about them as being locally isomorphic to analytic varieties. So something that's cut out by finally many analytic equations. That's a very rough definition. So if we have a local model for an analytic space, it means that we have some domain in Euclidean space, finally many equations that cut out that local model Y from that Euclidean domain. So these F's, these are the finally many equations that cut out the analytic set Y. And it, regardless of whether a point is a smooth point or not, it has any point has a Zariski tangent space. And we assume that we're given a smooth function, an analytic function F tilde on this smooth domain D that contains this analytic subvariety. And then we restrict this function F tilde to the analytic subvariety 1. And then we define something to be a critical point of F if we just have this inclusion. The Zariski tangent space is contained in that kernel. So so I threw in an assumption here that Y has a so-called invariant dimension, which is equal to the dimension of the ambient Euclidean space. And that means that P is also, if we have a critical point of F, it's also a critical point of F tilde, at least under that assumption. So next, we're going to assume that F tilde is Morse-Bott in the classical sense. So F tilde is a nice analytic function on a domain in Euclidean space. So Morse-Bott means that the critical set is just a connected real analytic submanifold. Its tangent space is the kernel of the Hessian. And then we're going to define subspaces of the Zariski tangent space according to whether or not there are positive, negative, or zero eigenvalue subspaces for the Hessian operator. All right, so given that setup, then we have the following nice conclusion. So if what I call the virtual Morse-Bott index is positive, and then P, this point P, is not a local minimum for F restricted to Y. So what makes this distinct from classical Morse index is we're subtracting off this number L. This difference in dimensions is something that's going to crop up over and over again, both in later generalizations of this theorem and also in the pictures that I'll describe. If you understand Kuranishi models or remember them from gauge theory, you should think about this L as the dimension of the so-called obstruction space in Kuranishi deformation.
Sorry, what is L again?
I will. So L is just the number of number of generators.
Okay.
Yeah. All right. So there is a global version of this theorem that simply replaces this local model by an analytic space. So it should not be surprising that this result will generalize to a global setting. The one catch is that we need f tilde to be a real analytic function on a smooth ambient manifold in order to state that global generalization. And fortunately, that's something that holds in practice. So if we're given a real analytic manifold, we're going to assume that we have a real analytic function on that manifold M that will serve as our Morse-Bott function on the real analytic manifold M. And then we're going to restrict that to an analytic subspace X, and then define critical points of F using an analogous recipe. And here, this is no longer the usual tangent space, it's the Zariski tangent space. Okay, so there's a little bit of rigmarole that one has to go through, and I will kind of spare you the details. But at the end of the day, let me get to the key formula, and I'll just try to talk around the formula. You can again define a virtual Morse-Bott index. This tangent space to X at point P, that's the Zariski tangent space. This GP minus, this is the subspace in which the Hessian is negative eigenvalue subspace. And in the language of Kurnishi deformation theory, this is the dimension of the so-called obstruction space. So if this quantity is positive, then again, the conclusion is this point P is not a local minimum. So it takes a while to properly explain this what this is. So I'll try to kind of hold off doing that, but I will give you some pictures at the end that hopefully get across the idea a little bit better. All right, so this gives you a way of telling whether or not a point is at least not a local minimum. So it's interesting from that perspective. However, the downside is that this quantity is rather difficult to compute. You would like to be able to say that this difference of dimensions somehow arises as a difference of dimensions of certain homology groups or cohomology groups. And then that would hint you that you might be able to compute this difference by applying a suitable index there. And with this definition here, you can't quite do that. So in Hitchin's paper, because he's dealing entirely with smooth manifolds, he noticed that he could apply a Riemann-Roch theorem to compute his classical Morse-Bott index, because all the other terms in his elliptic complex vanished. So then we had the idea, well, maybe some version of Hitchin's method works, even if not all other terms in the elliptic deformation complex vanish. So I'm going to define briefly so-called circle-equivariant version of this Morse-Bott index, which can be computed using the Atiyah-Singer index. So there's a version of Frankel's theorem, which I should explain, but I kind of gave you a brief introduction to it earlier, so I'll just kind of skip over the detailed version. So I'll just tell you the ingredients we need for this circle-equivariant theorem. So first of all, on this analytic manifold M, we need a circle action. We need a non-degenerate two-form that's circle-equivariant. Could be a symplectic form, it just doesn't have to be. It just needs to be non-degenerate. And a real analytic function that's Hamiltonian with respect to this sort of almost symplectic form. And then that combination of metric and symplectic form, they define an almost complex structure. All right, so with this setup, you can define a quantity that looks similar but is subtly different. Again, there is a Zariski tangent space, and then the Zariski tangent space kind of breaks up into a zero eigenvalue space, a positive, a negative eigenvalue subspace, and this is the dimension that's relevant here. And then rather than subtract off the dimension of the full Kurnishi type obstruction space, there is also in this picture a circle action that's induced on the Kurnishi type obstruction space, and that also splits up into a zero eigenvalue subspace, a positive eigenvalue subspace, a negative eigenvalue subspace, or more precisely, a positive weight subspace for the circle action, negative weight subspace, positive weight subspace. And it's this negative weight subspace that we're subtracting off. The significant thing is we're subtracting off something that's a smaller dimension than we were before. So it has a better chance to be positive, which is what we're interested in. And the key feature of this virtual Morse-Bott index is that if it's positive, then again, this point B is not a local minimum for this function on this possibly very, very singular analytic space. So this circle-equivariant virtual Morse-Bott index, it's a refinement of the previous one, though that's easier to explain. It may be positive even when the, its kind of simpler cousin is zero or maybe even negative. The other significant thing about this difference of terms is that these difference of dimensions can, in gauge theory settings, be interpreted as differences of dimensions of cohomology groups that arise in elliptic deformation type complexes for gauge theory equations. So projective vortex equations, Higgs monopole equations, and so on. And in that context, this virtual Morse-Bott index, if you can compute it now using the Atia-Singer index term. So in our monograph, we actually did compute this quantity for all of these Seiberg-Witten critical points that I described in the picture, and they're always positive. So kind of supporting the paradigm that I described earlier, that kind of pseudo picture of what's apparently happening in the moduli space of non-Abelian monopoles.
Yeah, does this circle action live on the whole modular space of non-Abelian monopoles or only over the Seiberg-Witten?
It lives even on the configuration space in which the moduli space lives.
It's just the diagonal.
It's induced by scalar multiplication on the sections. Yeah. Exactly like in the Hitchens paper. Okay, so let me kind of end with some pictures that try to, explain in silly examples, how some of the ideas work in the proofs. So there are two big ingredients in the proof. So one is resolution of singularities, and we normally think about that as being working for algebraic varieties or schemes and so forth. But Hironaka actually proved resolution of singularities for analytic spaces, as well as schemes and varieties and whatnot. The other notion we use is something called quantitative transversality. So as we'll see, it's important to be able to perturb unstable manifolds, if you will, that have certain transversality properties with respect to objects that are important in resolution of singularities. So key objects which are important in resolution of singularities are so-called blow-up centers and exceptional divisors, essentially the pre-images of blow-up centers. And quantitative transversality means that you can perturb certain subvarieties or submanifolds a little bit, but staying within certain prescribed or desired limits. And the pictures will kind of illustrate what I mean by that, or hopefully they will. So the first picture is very similar, just to explain what we mean by stable unstable manifolds. This simple picture of the sphere where we're looking at this critical point here with Morse index 1. And the M in the various theorems we had before is just 3 space and X, and this idealized model just a torus. Of course, this is smooth. We're interested in models which are not smooth, and we'll get to those in a moment. All right, so if we focus on a local model for the critical point in the behavior, the height function, if you will, I've drawn here the unstable, stable manifolds W plus, W minus. We're interested in knowing that near a certain critical point, that it's not a local minimum. So there's a silly observation you can make that you have actually cone neighborhoods of the unstable manifolds, where points lie below the critical point. So in our applications, we will want to be able to have the freedom to perturb an unstable manifold by at least finding a copy which is the same dimension as it and lying nearby, which lies within these cones of descent or whatever one might want to call them. And this is just the same cone of descent illustrated in this again this kind of silly picture. All right, so this is a smooth surface. What about something that's not smooth? So one of the first examples you'll learn about in introductions to resolution of singularities is how you resolve the quadratic cone. So here we have a nice surface in 3 space. M is 3 space in this picture, and just one singular point. So I'm assuming that we're given, I never specified, some Morse-Bott function on the whole 3 space, or at least an open neighborhood of this point. And F, as in before in the statement of the theorems, that's just a restriction of F tilde to this singular surface. All right, so now we apply resolution of singularities, and we get this picture. So here, X prime, this is the strict transform of the singular cone. E prime is the exceptional divisor. Their union is the so-called total transform. And P prime is just some point that's in the intersection of the exceptional divisor and the strict transform X prime that lies over the original cone point that was here in the previous picture. All right, so let's suppose then that we have, I'm going to assume that the tangent space of the unstable manifolds is this green subspace, this green plane here. And just for the sake of making the picture, since it's complicated enough already, easier, I'm just going to assume that the unstable manifold coincides on the nose with this tangent space. So you can think about this green plane here as being the tangent space to the unstable submanifold or just the unstable submanifold. And it happens to be transverse to the exceptional divisor. So it intersects the strict transform X prime in this nice curve here. And then when you project down to the original singular surface, this is what you get after you apply the resolution of projection, resolution of singularities morphism. So which is pi in this picture. You just need one blow up. So if you count dimensions, you find that the virtual. So we're not doing circle-equivariant anything here because that would just require a higher dimensional picture. So here, if you compute the virtual Morse-Bott index, it's equal to 1, and that corresponds to this intersection of unstable manifolds with X being positive. Now, you might go back to this picture here and object, well, what happens if this unstable manifold actually coincides on the nose with this exceptional divisor? Then when you kind of blow down, it'll just get swallowed by the resolution morphism. And that's where this idea of quantitative transversality comes in. That all you care about is you can kind of pull the unstable manifold away a little bit to find a copy that's close to it, but transverse to it. So you have this kind of, this unstable manifold, if it happens to coincide with B prime, you can find a nearby copy, W hat, let's call it, which does have this nice transversality and doesn't get swallowed up by the exceptional divisor when you project out. So in other words, in this picture here, you can replace W minus by a small perturbation and still know then that you're not at a local limit. Now, I mentioned here that the virtual Morse-Bott index was positive and that was important. So let's look at a case where the virtual Morse-Bott index is 0 and we can see what goes wrong. Oops, sorry about that. Wasn't intentional. Okay, all right. So here, unstable manifold, which has the same dimension as these tangent spaces. This is one-dimensional. And I'm drawing it here. It's transverse to the exceptional divisor. It's going kind of right through it and just intersecting at this point P prime. But in this example, the virtual Morse-Bott index is 0. And when you project down, of course, you just that unstable submanifold, it just gets swallowed. It gets the only residue of it, if you will, is this singular point here. So you don't know if you're at a local minimum or not. Oops, sorry about that. Sorry, that's not what I intended. All right, let me try to blow up this picture one more time. I realized when I was coming down here, it's been like 2 years since I gave a talk that was in person, and there we go. All right. All right. So here, virtual Morse-Bott index 0. And you notice that if this is the actual unstable manifold, that even if you look at an open cone neighborhood of this unstable manifold, that you could very well have a nearby line, if you will, passing through this point. So this is going to through this kind of negative cone, if you will, but you're still intersecting this strict transform and this exceptional divisor, simply at this point. So in this picture is trying to illustrate the fact that when you have Morse-Bott index 0, you no longer have this guarantee that a little perturbation will ensure that some copy of your unstable manifold will survive when you project down to the original surface. So in the previous picture, it was a little bit different because you have a locus here, which looks like it's in the smooth locus of the surface X, where you have points which lie below the critical point P, so you know that Morse function it doesn't have a local limit. All right, so thank you very much.
Questions for Paul?
Yeah, so the critical points are all the Seiberg-Witten. Is that right?
Yeah, well,
No.
they're all the Seiberg-Witten, and they're also the anti-self-dual points. Of course, if
We're looking for those.
you were looking for those, yeah. So it's the so that's important, yeah.
Right.
Yeah.
And the circle action now.
Yeah.
I mean, the only place where the circle action isn't the circle action has singularities only at phi 0. At the Higgs field being 0, right?
I mean, having fixed points, right?
Yeah. So
I'm sorry, fixed points.
yeah, fixed
I didn't
points.
say it.
Yeah. So the only there are two classes of fixed points where the field phi is 0, and then the Seiberg-Witten monopoles where the connection A is reducible.
Oh, okay.
Yeah.
So those but that's sort of less serious. Well,
it's not obvious, but there is a correspondence that's long been known between these pairs where the connection is reducible. It's known that those are given exactly by copies of Seiberg-Witten monopoles. So you can show
right. I see. I said so. You don't have it. Yeah, you don't have it reducible connect.
right. Yeah, those are the reducibles in this picture.
I see, but that's still. So even but the circle action, can't you just divide out by the circle action pretty much?
You can, yeah. I mean, you could quotient this moduli space by the circle
Right.
action, yeah. Except that from a topological point of view, in terms of Weyr-Donaldson invariance related to Seiberg-Witten invariance, that kind of story, it turns out to be that not quite the right thing to do topologically.
Oh,
And our use here is quite different because we're really trying to use the circle action and this an enhancement of this classical theorem due to Frankel, which relates Morse index, or in fact relates eigenvalues of the Hessian of a Hamiltonian function with weights of the circle action on the tangent spaces to fixed points. In Frankel's theorem.
Well, but the fixed points are all down at the self-two.
Oh, the Seiberg-Witten points are also fixed points.
Not of the circle action?
Yes.
Really?
Yeah.
Don't they have a spinner?
Yeah, don't they have a circle action?
Yeah, they do have a spin. Yeah, yeah. And they're only fixed points. It turns out they're only fixed points when the connection is reducible.
But doesn't the circle act on the spinner?
Yeah.
It does. Yeah, yeah. But there's also a gauge transformation there.
Yeah, well, there's a
right,
singularity
okay.
due to the gauge transformation.
Yeah.
Yeah, but not due to the circle action.
Right. Right. Yes. Yes. Yes.
Yeah.
Yeah.
So presumably this virtual Morse index, you compute it sort of algebraically from the local rings and things like that. That's the fixed point.
Yeah. So what happens is that the local structure of these moduli spaces, so non-Abelian monopoles and so on, they're defined, or they can be described by so-called elliptic deformation complexes, where there's a middle term, and H1 is essentially a risky tangent space. The H2 is a so-called obstruction space, and the H0 is a tangent space to the stabilizer of the gauge group action. And so that holds for any point in the moduli space. And when you're at a fixed point of the circle action, like a Seiberg-Witten point, that deformation complex splits into three components. So just like the Zariski, just like in classical Morse theory, where the tangent space splits into the plus space, the minus space, and the zero space, when you're at a singular point, the whole complex that's describing the singularity also splits. So the obstructions, all the terms in the elliptic complex split into plus spaces, minus spaces, and zero spaces. And if you look at the minus complex, you can compute its index using the Atiyah-Singer index theorem. And that's essentially what Hitchin did, except in his case, the only term that was non-zero was the tangent space term. The other terms which indicate some kind of singularity, those were zero in his application.
Yeah. Can you say a little bit about compactness? You need to have some compactness to know that the function attains its meaning.
Yeah, sure. Yeah.
So what goes into that?
Oh yeah. Well, that's a complicated story, and we're not done, with the program yet. So in terms of this picture, in terms of like what have we computed. So this picture I gave doesn't indicate any non-compactness because we get too complicated, but there will also be kind of ends of this moduli space MT which are not drawn in this picture. And what will happen is that when you compactify, you have two ways of compactifying using either Giesecke compactification in algebraic geometry world or the Uhlenbeck compactification in the gauge theory world. And you will end up with a more complicated but still singular space. So because this, but it will be compact. So because this notion of virtual Morse index applies to essentially any singularity, you can compactify and then compute the virtual Morse indices of all the points into compactification. So in our monograph, we compute the virtual Morse index of all the points, before you've compactified. And our expectation is that even after you compactify, that the new singular points that kind of, stick to the moduli space after doing the compactification, that they still have positive virtual Morse index too. But yeah, you're right. That's an extra step.
Or again.